Welcome to Biology for Bastards, teaching biology in the most profane way you have ever seen or heard. I'm your host, John Doty. Thanks for joining us. This season, we're going through the AP biology curriculum, one chapter at a time. And this week, or this episode, we are going through Chapter 3, Water. An entire chapter all about water. It's that awesome. Before we dive into it, however, a couple of things. Things have been pointed out where the last two chapters have been review. Chapters 1 and 2, things that you should know. We're finally getting into some new stuff. So the episodes might be getting a little bit longer. I'll be slowing down and explaining some of the science concepts in a little more detail and not just kind of blowing through them. So that being said, let's dive in. We're going to talk all about water for the next whoever knows how long. It's going to be fucking great. So it was mentioned in the last chapter about water being one of those polar covalent bonds where the electrons were not shared equally, giving a slight positive side and a slight negative side. With water, the oxygen is slightly negative. The hydrogen side is slightly positive. Just imagine like a Mickey Mouse looking thing. 2 ears are your hydrogens. Those are positive. There's 2 hydrogens, 2 lines and a plus sign. 1 oxygen, it's negative. And the important thing is you can get 4 different hydrogen bonds for every single molecule of water. Each hydrogen can make 1, and then the oxygen can actually make 2. And that's going to give water a shit ton of magic powers. There's an entire chapter about water. It's pretty special. And a lot of that specialness has to do with the fact that it can form all those different hydrogen bonds. So, a couple different magic powers of water. First, water has a very strong cohesive factor, cohesion. That's where we have the same substance sticking to itself, essentially. So this is responsible for surface tension. If you've ever done a belly flop, you know that water can be hard. If you've ever seen bugs walking on top of it, that is all due to the cohesive nature of the various molecules of water sticking to each other with those hydrogen bonds, doing their magic stuff. Okay, so cohesion, it's the same substance. Now there is something when it's different substances, and that's called adhesion. So that's when the molecules are different. So this is, in the case of water, like the adhesion of water and like the sides of a straw. Pulling up that, or if you stick like a towel in a thing of water, how it pulls itself up, the water pulls itself up the towel, that's because of the adhesion between the water and the towel. Okay, so cohesion is between atoms of the same stuff, or molecules of the same stuff. Adhesion is molecules of different things. These two things become very important when you start talking about transpiration and how plants get water. Because plants can be very, very tall. Think of a tree. And there's no pump pumping water to the top, even though the water has to get to every part of the tree in order for the thing to stay alive. So what ends up happening is there's this collective force of cohesion and adhesion that together pulls the water to the very top of the tree. The water is going to cohesively stick to each other, and it's going to adhesively stick to the sides of these magic tubes called xylem, and it will pull the water towards the top. That's fucking magic. Think of it as like the best towel ever. Like Bounty ain't got shit on the transpiration powers of trees. If you think about like the giant sequoias, those things are like fucking tall. I don't even know how tall they are. I was going to make up a number, but I don't want to short sell them. I might make up a number that's too small. They are huge. You can drive cars through them. and yet they get water to the very top without any pump whatsoever, just cohesion and adhesion. That's pretty magical. All right, next up, water has a very high specific heat, which basically means it can absorb a lot of energy without changing temperature. If you've ever had a pool, or gone into water after it's been warm in the summer and the water's still fucking freezing, it's because of that high specific heat. Okay, now what heat is how much kinetic energy there is within a system. A system is just something that you're looking at. So when we talk about the kinetic energy, that's the energy of movement. So how quickly the particles are moving. So heat is different from temperature, because temperature is an average of all the heat there. So that's why, if you spill some water, the water can evaporate even though it's not boiling, because different molecules will have a high enough heat to turn into a gas and float away, but the overall average measure of heat for all those molecules might only be 80 degrees, 70 degrees. But there's enough heat there for some molecules to be able to make that transition from liquid to gas and disappear. So water, like I said, has a very high specific heat, which is really helpful. But to put it in perspective, you think of something like iron, like metal gets hot really fast. It's got a specific heat that is 1/10 that of water. Alcohol is about half the number that water has. So water is really good at maintaining stable temperatures. And that's really fortunate for us being water-based, because as our temperature doesn't go up or go down because the water's there stabilizing everything. And when our temperature does get too high, we sweat. And sweat is a type of evaporative cooling. Because water has a high specific heat, because it can store a lot of energy, because of all those hydrogen bonds it can form, when water turns from a liquid into a gas, it takes a lot of energy with it. And that energy is in the form of heat. So when it goes away, a lot of heat goes with it. So we sweat, and as that sweat evaporates, it's pulling the heat away, which is why you feel much cooler if you're covered in sweat and then you stand in front of a fan. It's pushing all that super energetic sweat off of your body. You feel very, very cool. And that, just by math, makes the rest of everything, the temperature of everything else, go down. Because if you take the hottest molecules, the ones with the most energy, and you get rid of them, the average amount of energy the rest of them have go down. Simple as that. Okay, it's just like if you take the top 10 best performers on a team and you get rid of them, the rest of the team is going to suck. It's going to be garbage. So we do that. We sweat. Plants can also do stuff like that. They can transpire and let water go through their leaves. And then lastly, kind of getting into it, is water, by being polar and having all those hydrogen bonds, it is an extremely versatile solvent. So what that means is when you have a bunch of liquid, okay, that's called a solvent. Okay, because in that you can dissolve stuff. That dissolved stuff is called the solute, and together that gives you a solution. So it's a combination of two substances kind of in solution. Okay, we call it aqueous solution if the solvent is water. Most of the times in biology, it's definitely going to be water. Very rarely is it not water in biology. Now in chemistry, you can use, benzene, alcohol, other fancy chemicals, but biology, we keep it simple, water. Okay, so water's the solvent, solute's the shit that gets dissolved, and the solution is the shit you get at the end. Now, with ionic compounds, and remember ionic compounds, going back to the custody thing, have full custody of the kid, the other gives up parental rights. So there's a positive, there's a negative, they're stuck together like a magnet. When you throw them in water, those parts separate out. That's what happens with salt. So the positive, so in salt it's sodium chloride, sodium is positive. It gets surrounded by all the negative sides of the water. The chlorine gets surrounded by all the positive sides of the water, so all the hydrogen surround it. And you make little hydration shells, as they're called, around all the individual ions. Now when you get something bigger, or you get something non-ionic, so a covalent thing, you can still dissolve it because the water molecules will form that hydration shell based on polar regions or ionic regions on the bigger molecule. So even though the big thing that you're dissolving, say sugar, is not an ionic compound, you can still dissolve it in water because the water is going to surround it and make that shell and essentially hide the sugar from everything else. So it's going to team up with the water. You'll have this hydration shell effect thing going on, and the sugar just disappears. Okay, so with this water and with these solutions, there's this idea that is necessary to understand called molarity. It's a chemistry term. And I know, chemistry fucking sucks. It is totally not biology, and biology is so much better, but this is one that is kind of important. Okay, and it's really easy to figure out because the definition of molarity is how many moles of a solute per liter of solution. And you can get into a shit ton of detail in chemistry with this. So you got to think about displacement and this and that and all that other shit. But in here, we're going to keep it pretty simple. You do need to know what a mole is. So a mole is 6.02 times 10 to the 23rd. It's a unit. Think of a mole as a dozen. A mole is a shit ton more than a dozen, but it's the same idea where we have a word to describe a certain number. So molarity is the number of moles. So just how many dozen of solute do you have per liter of solution? So in order to do this, you have to know the molar mass. And what that is, you use a periodic table and you just add up all the different atoms that are in it in whatever molecule you're looking at. So let's say we're looking at glucose that has a molecular formula of C6H12O6. So you have carbon, which has a mass of 12 times 6, hydrogen, which has a mass of 1 times 12, and then oxygen, which has a mass of 16 times 6. So you just add up all the different atoms in it, and that gives you a number. In the case of glucose, it's 180. So 180 is the molar mass of glucose. If you're making a 1 molar solution, you take 180 grams and then add enough water to get up to 1 liter. And that's a 1 molar mass, a 1 molar solution. Now in the PowerPoint that will be up on the show notes, there's a couple other examples. I'm not going to spend too much because it's the same idea. If you make a 2 molar solution, you take 2 moles and add it to 1 liter of water, or enough water to make 1 liter. Don't add it to 1 liter of water because the displacement, that won't technically be 2 molar solution. You add enough water to get to 1 liter. Or if you are going to make half a liter, you add it to, or half a molar, sorry. Do half a molar solution, you take half of a mole to 1 liter. There's some math up there that you can look at. That's why I put the show notes up there, or put it in the show notes. All right, last main idea is acids and bases. So far we're not going too much longer than the other episodes. Like I said, they'll change as we get further into stuff and get into more complex concepts These are all pretty straightforward and just kind of vocab-y type things, not really sit down and think about stuff. That'll change soon. Okay, so the last concept we've got to talk about are acids and bases. Okay, not that type of acid that you drop and have crazy trips and whatever. Not that stuff. Acids, as in, like, theoretically could burn your face off. Bases can do that too, though. You'll find out. So, with water, H2O, it'll dissociate into two parts. Into an H+, we call that either a hydrogen ion, or sometimes we say it combines with another water and it's a hydronium ion. And then we have an OH-. That's a hydroxide ion. It's the oxygen and the hydrogen kind of left over. So it splits into the plus, H+, and it splits into the minus, OH-. Now when we have different substances in solution, an acid is anything that will increase how many H+'s there are in that solution. So something like hydrogen chloride, HCl, that's going to add a lot of H+ to it, so that is an acid. A base is the opposite. It's going to reduce the amount of H+'s. So something like sodium hydroxide, that's Na, so that's sodium, OH, that's hydroxide. That OH is going to team up with the free-floating hydrogens, the H+'s that the water turns into, and it's going to reduce how many H+'s are actually there. So it's going to be a base. Okay. Yeah, so with the pH scale, it is a measurement of how many of those H+ ions there are in a solution. Now, don't get me fucking started on the pH scale, because it's weird math. It's logarithmic, which I don't understand how logarithmic math works. I know it's a factor of 10, so 7.1 to 7.2 is a factor of 10, I think. I don't fucking know. Really? In biology and what we're going to talk about, it's not a huge fucking deal. That's a secret. Okay? The pH scale is just something that is not a huge deal. Because in life, we as humans are at a 7.4 pH. If we drop down to a 7, or we get up to like a 7.8, we are dead. It's just that simple. So your stomach acid is very acidic, has a very low pH. Okay, because the lower the number, the more acidic. 7 is right in the middle, that's neutral. 0 to 7 is an acid. And if you get really low, like 0, 1, 2, those are strong acids. And then 7 to 14, those are bases. And if you get real high, 11, 12, 13, 14, those are strong bases. But biology doesn't deal with those strong acids and strong bases much, because they are very, very, very harmful and they will kill you. Okay, so what we do is we have these things called buffers, which I don't understand buffers. I never have. I never will. Hopefully, take chemistry, figure that shit out, because I can't help you. All I know is that a buffer, if you have a strong acid added to it, it makes it not strong. If you add a strong base to it, it makes it not strong. It's some fucking witchcraft that like cancels the other thing out. So you can pour a strong acid or an acid into it and it stays neutral, or it barely changes to acidic. And then it also works with the opposite with bases. So I don't get it. I don't know. All I know is that without them we would be dead. So yay buffers, and they're fucking witchcraft. That's about it. Okay, so with that, that brings us to the end of this episode. I really like this last slide up in the show notes, because it kind of sums up everything. Cohesion, adhesion, surface tension, specific heat, the evaporation and cooling, and the universal universal solvent. All these magic properties of water that are all, caused by the hydrogen bonds that it can form. Now, I did skip 2 examples of pH and the effect on the environment. One is the acidification of the ocean. That has to do with carbon dioxide reacting with water, making this carbonate, which then turns into a carbonic acid, which is an acid, and it's going to lower the pH of the water, and it's going to kill coral and all this other stuff. Because just like us, if their pH gets too out of whack, they're going to die. But unlike us, they live surrounded in solution. So they're a little more sensitive to it than we are. So that's why all the coral reefs are dying, because of all the carbon dioxide in the air. So we're all fuckers for doing that. And then the other one is acid rain. Acid rain is not super strong acid. It's just slightly more acidic than regular, but that builds up in the soil, and that can have big effects on the plants because, as we talked about, it pulls the water to every bit of the plant. And just like us, if they can't buffer that stuff out, or it's just too much, then they're gonna die. So that is your chapter all about water. It was a hoot, wasn't it? Okay, kind of keeping on that vein of talking about one substance in particular. The next episode is going to be all about carbon. You've probably heard of that word, carbon-based life. We'll find out what that means and all the magic powers of carbon, and do a little organic chemistry in the next episode. But until then, this has been Biology for Bastards, teaching biology in the most profane way you've ever seen or heard. I'm your host, John Doty. Please rate, review, subscribe, tell everybody you know about it. If you want to say anything to us, we are up on Twitter. We are at Bio for Bastards. Send us something, say hi, give us a follow there. And until next time, thanks for listening. Damn it, I forgot to credit our music again. So our intro and outro music is Feeling Good by Purple Planet Music. Got to do that each time. Otherwise, I'm in violation of the law, and that's bad. Also, if you heard any weird noises this episode, those were probably the dogs barking. No apologies for that. They're dogs. So, again, thanks for listening.